In this video, we are going to talk about one of the most important logic families, specifically the complementary MOSFET, or we abbreviate it as CMOS, complementary MOSFET. In particular, we are going to discuss the CMOS inverter, the complementary MOSFET inverter. And the complementary MOSFET inverter consists of two MOSFETs. One of them is NMOS and the other one is PMOS, connected as following. So here, this is the PMOS transistor, and this is the NMOS transistor, and then we connect the two gates together to the input, and we connect the two drains together to the output. So the input is the voltage of the gate of both transistors, and the output is the voltage of the drain of both transistors. So this is a PMOS, and this is NMOS. Let's mark the drain and the gate of each of them. So this is the gate, this is the gate here, this is the drain, this is the source of the NMOS, this is the drain, this is the source, this is the gate of the PMOS. And from the bottom, it's connected to ground, up, it's connected to a voltage source called VDD. So this is basically how the CMOS inverter looks like. Just two transistors with gates connected together, drains connected together. The input is connected to the gates and the output is connected to the drain. The purpose of this lecture is to draw the characteristics, the transfer function between the input and the output of this circuit, and to show that the relation is the same or very similar to be an inverter. So the purpose of this lecture is to plot eventually a relation between the input and the output. In order to do that, we'll have to study the characteristics of the NMOS transistor and the characteristics of the PMOS transistor. We already studied them, so we're going to just review them quickly, and then we apply the current connection to these characteristics that we studied before. We remember that we talked about the characteristics of the NMOS transistor, and we said that for the NMOS transistor, we have the relation between IDS and VDS to be set of curves that look like this, right? In the beginning, for VGS less than V threshold, the transistor is off and the current is 0. So this is for VGS less than V threshold. And then as you increase VGS above V threshold, you go up in these curves. So for example, if V threshold is 1 volt, then for VGS less than 1 volt, the transistor will be off. VGS equals 2 volt, you will be here. VGS equals 3 volt, you will be here. VGS equals 4, 5, and so on. So you will get a set of curves that look like this. For VGS less than V threshold, it will be 0, the transistor will be off, and then as you increase VGS, you are going to increase. This is for the NMOS. For the PMOS, we can get exactly the same set of curves. However, instead of IDS, it will be ISD, and then instead of VDS, it will be VSD, and instead of VGS, it will be VSG, right? So we can have this set of curves. Let's plot it here. Let's plot it here now for the PMOS, and instead of IDS, it will be ISD, and this will be VSD. And then we say that for VSG less than the negative of V threshold P, then the transistor will be off and you will get a 0 curve, okay? And then as you increase VSG, you will get set of curves that look like this. So as you increase VSG of the PMOS, I'll write P here. As you increase VSG, the curve goes up. here as you increase VGS of the NMOS, VGS of the NMOS, as you increase it, the curve goes up. So these are the characteristic curves for the NMOS. These are the characteristic curves for the PMOS. We studied this before. Now let's apply this to our circuit. So, for example, we will notice what? We will notice that for the NMOS, VDS is the same as Vout. So VDS of the NMOS is the same as Vout. So we can replace VDS here. We can replace VDS here with Vout. And VGS, so this is VGS, VDS is the same as V output. And VGS is the same as what? VGS is the same as V input. So here we say that if V input is less than V threshold, you will get a zero curve. And as V input increases, you will get a higher curve. This is for the NMOS. So we wrote the same set of curves, but in terms of V input and V out. And by the way, before we continue, the current of the NMOS, IDS of the NMOS is the current here. Is the same as the current ISD of the PMOS. ISD of the PMOS is the current from the source to the drain. And the IDS of the NMOS is the current from the drain to the source. So we are going to call it I. These two currents, IDS of the NMOS and ISD of the PMOS, both of them are the same. So we are just going to call them I. Now, we wrote this set of curves in terms of V input and V out. Let's move to the other set of curves. VSD of the PMOS. What is VSD of the PMOS? Let's use another color. VSD of the PMOS is this voltage. This is VSD of the PMOS. It is equal to what? It is equal to VDD minus V out. So VSD of the PMOS equals VDD minus V out. So we can replace VSD of the PMOS here with VDD minus V out. And then VSG of the PMOS, is the voltage here between this point and this point. This is VSG of the PMOS. It is equal to VDD minus VM. So here we replace VSG of the PMOS with VDD minus VM. And also this one, we replace it with VDD minus VM. So we say that as VDD minus V input increases, we go up in the curves. Here we say that if VDD minus V input is less than negative V threshold P, then you will get a zero curve. So now, in order to just have a look at these two curves, we need both curves to be plotted with the same axes exactly. The curves for the NMOS and the curves for the PMOS, we need them to be plotted with the same axis. So the vertical axis is the same in both of them, I and I. But the horizontal axis here is V out, while the horizontal axis here is VDD minus V out. Here the curves are increasing as V input increases. Here they are increasing as VDD minus V input increases. By the way, let's start with the easy thing. When we say that the curves here, they increase or we go up in the curves as VDD minus V input increases. This means what? This means that as V input decreases, we go up, right? If we go up as VDD minus V input increases, this means that we go up as V input decreases. So we can write the following. We can say that as V input decreases, we'll go up in the curves here. Or in other words, you can say that as V input increases, we will go down. So we can write it also like this. As V input increases, as V input increases, you will go down in the curves here. The curve will go down, right? Because as V input increases, VSG decreases, and hence you will go down, right? So as V input increases, you will go down in the curves until you reach where? Until you reach that V input is higher than, until you reach that V input is higher than VDD minus negative V threshold. And I insist to write it like this to avoid any confusion. So until V input is higher than VDD minus the negative value of V threshold, okay, then you will get this curve, the zero curve. So now we can remove this condition, and we say that when V input is higher than VDD minus V threshold, you will get the zero curve, okay, and as V input increases, you go down. Now, remaining thing is that the horizontal axis here is V out, the horizontal axis here is VDD minus V out. So I'm going to ask you a question, and maybe those who studied the signals and system will be able to answer it quickly. If I have a curve plotted with VDD minus V out, and I want to plot it with V out, what should I do? So I have this curve or set of curves plotted with horizontal axis VDD minus V out. And I want to plot it, I want to plot the same set of curves, but instead of the horizontal axis being VDD minus V out, I want to plot it with V out. So this is for the PMOS. What should I do? If you think about it, you will find that if you have a curve plotted with VDD minus V out and you want to plot it with V out, first you have to reverse the curve, reflect it to the other side, and then you shift it by VDD. So you shift it by VDD. So you will get, first you reflect the curve like this, you reflected the set of curves like this, and then you shift them by VDD. So what you will get, and this is something from you must have studied in the signals and systems course, you will get, if you want to plot the same set of curves but with V out, you will get set of curves that look like this. And this point will be VDD. So you reflect and you shift by VDD. So these curves will be for the PMOS. We already wrote it. So these curves will be for the PMOS. And again, as V input increases, you go down. As V input increases, you go down until here, when V input is larger than VDD minus the threshold, minus negative the threshold value of the PMOS, then you will get the transistor, the PMOS will be off, and you will get the zero curve. So now we have the set of curves for the NMOS plotted between I and V out, and the set of curves for the PMOS plotted between I and V out. And now we don't need this one. We can remove this one. All these are steps that we need in order to plot the final curve that we want between V out and V in. Now, we have this set of curves between I and V out for the NMOS, and this set of curves between I and V out for the PMOS. Let me ask you a question. Now, when V input is less than V threshold, so now we are going to combine both of them here, I and V out. When V input is less than V threshold, the NMOS is going to operate on this curve, which is zero curve, right? So the NMOS is going to operate on a zero curve. So when V input is very small, less than V threshold, the NMOS will be operating here on this curve. While the PMOS, when V input is very small, it will be operating at a very high curve, right? When V input is small here, you will be at a high curve. So the PMOS will get a curve like this. So this curve will be from the NMOS, and this curve will be from the PMOS. Here, the NMOS says that this curve must be satisfied. This curve between I and V output must be satisfied. And the PMOS says this curve between I and V output must be satisfied. And I is the same. I for both is the same, and V output for both is the same, right? So the NMOS says I must work on this curve, and the PMOS says I must work on this curve. So where will they work? They will work on the intersection between the two curves, because the intersection point is the only point that satisfies this curve and this curve, that satisfies the NMOS curve and the PMOS curve. So both of them, they are going, so here as V input is less than V threshold, this will be the case. The NMOS wants to operate on a zero curve, while the PMOS wants to operate on a high curve. The only point that satisfies both of them is the intersection point, which is VDD. The output will be VDD. So here we start by saying that when V input is less than V threshold, when V input is less than V threshold, the output will be VDD. The output will be VDD, the intersection point here. The intersection point, the output will be VDD. Okay, now think about the next step. If we increase V input a little bit above V threshold, when we increase V input above V threshold, then the NMOS is going to operate on a curve higher than zero. So the NMOS is going to operate here, for example. The NMOS will say, when we increase V input above V threshold, the NMOS is going to say, I want to operate on this curve. While the PMOS, as we increase V input, we go down, right? In the PMOS, as we increase V input, we go down. So the PMOS is going to operate on a lower curve. So the PMOS is going to operate on a lower curve. So this is the NMOS. It will start to operate with a higher curve than zero, while the PMOS will operate on a lower curve. So this is what's happening. As we increase V input, the NMOS will start to increase, and the curve of the PMOS will start to decrease. In the beginning, they were like this. As we increase V input, the curve for the NMOS is going to increase, and the curve for the PMOS is going to decrease. Now the operating point will be here. In this operating point, V output will start to decrease, right? V output will start to decrease below VDD. So if we study the equations, you will find that you can get a quarter of a circle. The equation will be a quarter of a circle like this. V input, as you increase V input above V threshold, and V output will start to decrease, and it will take this quadratic shape of a quarter of a circle. And in this region, the NMOS is operating. The NMOS is operating in the saturation region, and the PMOS is operating in the triode region. So here we say that the NMOS is saturation and the PMOS is triode. Before we forget, in the first region, the NMOS was off and the PMOS was triode. In the first region, the NMOS was off. Let's write it in black. The NMOS was off. And the PMOS was triode. Then, when you increase V input a little bit more, the NMOS became saturation and the PMOS triode. And if you want to write this equation, all what you need to do is equate the current for the NMOS and the PMOS. The current is the same in both of them, but the current, equate the current of the NMOS in saturation to the current of the PMOS in triode. And I'm going maybe to do it one time here. the current of the NMOS in saturation is Kn over 2 VGS minus V threshold all squared equals the current of the PMOS in triode, which is Kp. Instead of VGS, it's VSG minus V threshold P minus VSD over 2 multiplied by VSD. And then you replace VGS of the NMOS is the same as V input, so you replace VGS with V input minus V threshold squared equals Kp. VSG of the PMOS is VDD minus V input minus V threshold P minus VSD of the PMOS is VDD minus V output over 2 multiplied by VDD minus V out. And then you find that you get a relation between V input and V output. It's a quadratic relation. This quadratic relation, if you expand it and you simplify it, you will find that it will give you a quarter circle relation. You will get a relation of a circle, an equation of a circle, and if you apply it here, you will find that you will get a quarter of a circle. Quadratic relation between V input and V output, and it will give you this part of the curve. Next, what do you imagine that it will happen if we increase V input more? So the NMOS curve is here, the PMOS curve is here. If we increase the input more, the NMOS curve is going to increase and the PMOS curve is going to decrease until they overlap, right? So if you increase V input more, the next case that will happen, that you will get a curve for the NMOS like this, and a curve for the PMOS like this, and then they will start to overlap in a big line. The operating point here, it will not be only one point. The operating point will be the overlap, this whole overlap, right? So here both of them will be saturation, and the operating points will be, all these points are operating points. So all these points for V out will be operating points. How to represent this on a curve like this? We represent it by a vertical line. A vertical line. All these operating points, all these values for the output will happen at this operating point, at this V input, at this exact V input, which we can calculate later, okay? We call it, let's now call it V threshold, okay? Different from VTN and VTP, V threshold in the middle. All these operating points are values for the output, right? Possible values for the output, possible operating points. So how to represent them? We represent them by a vertical line here, where this vertical line says that at this input, all these outputs are possible. And you can imagine this, I know it might be confusing, but you can imagine this as, this is the NMOS curve, and this is the PMOS curve. In the beginning, they will intersect here at the edge of saturation of the PMOS, and then they will overlap. When they overlap, all these points are possible, and then directly the point after it will be here. The operating point was here, and then they will overlap, and then directly the next point will be at the other side. So in the beginning, just before this overlap, the operating point was here, and suddenly, if you increase V input more, let's plot it in blue. If you increase V input more, you'll find that the curve of the NMOS will be higher, and the curve of the PMOS will be lower, and you'll find that you will move here. Suddenly, the output will move from this point to this point, to the other side. And this is what happens in this curve. The output suddenly will move from being at this point to this point suddenly. Just before V threshold, it was here. The operating point was here. directly after V threshold, the operating point was here. Let me clean this a little bit so that you can see. So here what we say is, as you increase V input more, we reach to the state that both curves will overlap, and both of them will be saturation. So the green curve here, both NMOS and PMOS, both of them will be saturation. If you increase V input more, the curve for the NMOS will go up, and the curve for the PMOS will go down, and V output suddenly it will move to be very low, and at this region the NMOS is operating in. At this region, the NMOS will be operating in the triode, and the PMOS will be operating in saturation. So here you will find that you will get a relation between the input and the output, where here in this region the NMOS will be working in the triode and the PMOS will be working in saturation. And again, similar to this part of the curve, you can get, if you equate the current of the NMOS in triode to the current of the PMOS in saturation, you will get a quarter of a circle that looks like this, quadratic relation that looks like this, until you reach this point. And this point happens when you increase V input more and the PMOS turns off. Let me take the black again. This point will happen when you increase V input more. The curve for the NMOS will go up, and the curve for the PMOS will go down, and the PMOS will be off while the NMOS will be with a high curve. And this happens, the operating point will be here, and this happens when V input is enough to turn the PMOS off. When V input is greater than VDD minus negative VTP. Once V input reaches to this value, the curve for the PMOS will be 0, and the curve for the NMOS will be high, and the operating point will be, of course, 0. The intersection between the curve of the PMOS and the curve of the NMOS will be at the 0, and in this case, V output will be 0. And again, this happens when V input is greater than VDD minus VTP. Okay? And in this region, the NMOS will be triode and the PMOS will be saturation. The PMOS will be off, and the PMOS will be off. And like this, we plotted the curve between the input and the output at different regions, at different inputs. Okay? And in each input, for each input, we found the region of operation, the point of operation, and the region of operation for each transistor. So in the beginning, when the input was very low, the NMOS was off and the PMOS had a high curve, very high curve. And then when you increase, the operating point will be here, saturation of the NMOS and triode of the PMOS. And then both of them will be saturation. And then if you increase the input more, you will get the operating point at the saturation of the PMOS and the triode of the NMOS. And then if you increase the input more, the PMOS will be off and the NMOS will be triode, and the operating point will be 0 output. So this is now the curve, the relation between V input and V output, the transfer function between V input and V output of the CMOS inverter. We'll stop this video here and we'll analyze this curve and talk about it more in the next video, inshallah.